Hello, welcome to the 12th lecture of the course, where our agenda is to discuss the proof of the Lovasz local lemma. Okay. In fact, we will see three variants of this lemma and we will prove each of them. The proofs all have the same idea, but the details get slightly more complicated. The basic idea you will see in the first proof itself, but then we will optimize it in the second and the third proofs. Okay, it's a very good proof. Not a. If you remember the other tricks that we have used in this course so far, like the union bound, the proof is obvious if you think about the Venn diagrams, right? And the linearity of expectation is also obvious if you think about it. What is the average of math plus physics marks in a class? It is the average marks of math plus average mark of physics, provided the class remains the same. Okay, so this linearity of expectation, that's all quite easy to prove. In fact, that's why we did not even spend time discussing the proof of that. But Lovasz local lemma, on the other hand, is a very non-trivial claim, and hence its proof is also not straightforward. Okay, so that's why I thought we'll do three variants and prove each of them, so that we get to see that main idea multiple times. So let me remind you what was the form in which we used the Lovasz local lemma in the previous class. The context was that we had a collection A1 to AM of M events such that each AI is mutually independent from a large set. Okay, and this is the only way to, because of this word mutual, it was not correct to call that AI's dependency was in some sense curtailed, but at least to keep my talking smaller. That is intuitively the idea. Okay? If our AI has a dependence on the other, it is limited to within a set of size D. That's the context, and we needed this inequality to be satisfied by P, where P is a bound for all P of AIs for all AI, and this P had to be at most 1 by E times D plus 1. Okay? Actually, I can combine these two, and then this I can 2 plus 3 is nothing but a bound on P of AI, right? We are just saying P of AI is at most reciprocal of D, but not exactly reciprocal of D, but 1 by E times D plus 1. And then we will get the conclusion we want. The conclusion that we are looking for is that the union of AIs has a probability strictly less than 1. Okay. Remember that the strictly less than 1 is the only non-trivial part in this conclusion, right? Because if I put a less than or equal to here, then that's a trivial statement, because any probability is upper bounded by 1. Okay. So the entire use of this conclusion is only because there is a strict inequality there. Okay. Now let's go to the three versions of the lemma and the three proofs. But before we do that, there is some notation that we will introduce, which we will use in all the three proofs. Okay. So before going into the proof, we'll spend 5 minutes familiarizing with this notation. Not anything difficult or anything, but just if you remember this notation when you hear the proofs, it would be far easier. If you have to then come back and refer to this notations again, because the proof is already going to be a bit complicated, it is recommended that you memorize these notations. Okay. So for each event AI, I'll denote its complement by BI. This is more just to make the reading more legible, because we are going to mix this AIs, AJ complements and so on in many of the expressions, and maybe this bars may go unnoticed. Okay, so in order to emphasize or to be notationally clear as to whether we are talking about AI or its complement, I'm using this BI for that. Okay, now I'm going to define this DI and MI. But these DI and MI are not in the same context as events. They are just subsets of these indices. Okay, so we have M events, which means when you name them as A1 to AM, the subscripts range from 1 to M. Okay, so this DI and MI are two subsets of this range of indices. Okay, and since there is one DI for each I. So D1 may be different from D2, it may be different from D3 and so on. But what is DI and MI? So you fix an I, okay, the collection of events to which AI, that single event AI, is mutually independent, the subscripts of those events, if you take this set of events to which which this lemma guarantees here. It says that it is mutually independent to a subset of at least so many events, right? Those events you take, but then you only read their subscripts. That is what your set Mi is, okay? So remember two things about Mi. Mi is a subset of indices, not a subcollection of events, okay? So remember that also. Both Mi and Di, okay? Mi and Di are subset of indices, okay? Not collection of events, not subcollection of events. Otherwise, some notational confusion will be collection of events, okay? And so mu I is those subscripts such that the corresponding collection of events is mutually independent from Ai, and Di is in fact the whole list of subscripts minus I minus Mi. In fact, that's the best way to define Di, because if I intuitively, Di is that Di denotes the subscripts of that collection of events on which Ai may depend, okay? So that's why I use the letter D and so on. But if you want to formally define these, first define Mi and then define Di as the range M minus I minus Mi. Note that this I here is neither in Di nor in Mi, okay? So M is in fact split into 3, the singleton I, then the dependent guys to Ai, their subscripts is Di, the independent guys to Ai, their subscript is Mi. Okay, so this also we will use. Okay, and then we will also use this notation, something like B subscript Di, to denote the intersection of all the events indexed by indices inside of Di. Okay, so yeah, this expression you can see. Similarly, I can define BMI. In fact, this kind of a notation is very standard, and we can use it for we can use it for any subset S of indices, right? So if S is a subset of indices by subset of M, this 1, 2, 3 up to M is what I call as 1, 2, 3 up to M is what I call as the indices, subset of indices. Then B of S is nothing but the intersection of all the events B. Remember, B is the complement of A indexed by the subscripts in S. Okay, so if I write something like B357, this will actually mean B3 intersection B5 intersection B7. Okay, I also want you to check what is B5. Pause for a moment and think about it, and the answer will turn out to be omega. Okay, the empty intersection, an intersection of no events, is actually the universal event. It is something like equivalent to saying an empty product is 1 and so on, but you can either reason it out, or else you can even think of it as a convention, which is just not the best thing to do. I think you should actually reason it out and think that B of the empty set will be omega itself. Okay, so this is about the notation. Now remember, what is our aim? Our aim is to show that the union of AIs has a probability strictly less than 1. But in all the proofs, instead of showing this, we will show something equivalent to this. Okay, so that's what I call by this, that's what I mean when I say that we are massaging the aim, right? So this is what we want to show, that the probability of the union is strictly less than, okay, remember the strictly less than 1. Now, this is equivalent to showing that, in fact, there's a two-way implication. This is equivalent to showing that the intersection of BIs has a strictly positive, again the strict is important, has a strictly positive probability. This is just De Morgan's law. In order to show that this union event has probability strictly less than 1, it is enough to show that its complement event has probability strictly greater than 0. And if its complement event, if you expand it using De Morgan's law and replace and just denote each AI complement by BI, this is what you get. Easy to verify, okay? If you are, you should verify it, but it's easy to verify. Now, but again, this is not what we will prove. If we prove this, this is also enough, okay? But again, we will prove something which will imply this, okay? So what is this P? This is a probability of an intersection of a collection of events. So which, if you know the conditional probabilities, you can write it this way, right? P of B1 times P of B2, given that B1 has already occurred, times P of B3, given that B1 and B2 has already occurred, and so on. Okay, so in some sense, this is extended version of the definition of conditional probabilities, right? This also you should actually just pause and verify. All you need is this general definition that P of CD is equal to P of C given D is equal to P of C intersection D by P of D, or if you rewrite it, P of C intersection D is actually it is I should have written it for D given C so that it is the alphabetic order makes sense. So the probability of the first event times probability of the second event given the first event, and so on. Now you extend it to m events, you will get this formula. Okay, this also you have to pause and verify. Okay, yeah. And hence, since what is our aim? Our aim is to show that this guy here is positive, strictly positive, which we can show, which we can conclude if each of these events, each of the terms in this product is strictly positive. Right? There are only finitely many terms, so a product of strictly positive quantities will be strictly positive. So hence, it is enough to show that for each I 1 to m in this range, these terms, okay, which if I write it as a single, if I denote it by some common index I, it is P of Bi given the B events up to I, not including I. Okay, so Bi given B1 intersection all the way up to Bi minus 1. Okay. By the way, this I can even denote it as some Bi minus 1 if I need it, but I did not. Okay. Right. So this is the event that we will have. So if each of these, for now, note that here earlier we only wanted to show one event had a strict positive probability, but now we have to show some m conditional probabilities are strictly greater than 0, and it looks like we are increasing our work. But you will see why this helps. Okay, in fact, our proof is going to be by induction, so this is not a problem. Okay, and now we again go back from this greater than 0 to strictly less than 1. We are finally, I mean, this is I promise you that this is the last modification in the last step in this massaging the aim. Right? What we do is that instead of showing P of Bi given these, the complement of that within the conditioning, okay, which is probability of Ai given the same thing is less than 1. Yeah, this also I'll leave as a verification exercise. But again, what is the soul of it? What we are saying is that if you have some, you can write something like P of C1 union, okay, or something like, P of C complement given D is 1 minus P of C given D. Okay, you can verify it in two ways. Either you can just expand these expressions and check this is correct, and hence proving that this guy is strictly less than 1 will prove that, in fact, this is also an equivalence, will prove that this guy is strictly positive. Okay, but I would rather want you to verify it pictorially. Think about this. This is the universal set, and let's say this is your D. Then you should, and let me draw C also. This is your C, right? Then what is this P of C bar given D? That is actually the amount, this area, in the ratio of this area inside D. It is not this area, it is this area divided by area of D. Okay, C intersection D by D. And what is this area then? This is what this P of C bar given D would be, right? That is this area again as a ratio of PD. But now if you add these two ratios, you cover entire PD. But since we are talking about the fraction of PD, it will be 1. Okay, so I want you to verify this in both ways. I want you to verify this by maybe expanding the expression for, using this definition of conditional probability. But more importantly, I wanted you to verify this using these pictures. Oh, okay. I think I have to slightly go back on my promise. I said this is going to be the final step in the massaging of the aim part. But since I'm going to prove by induction, I'm going to prove it in a slightly more generality. I'm going to show that P of AI given Bs, which is intersection of any collection of these complement events. Okay, here we are talking about a particular case where S is 1, 2 up to I minus 1, or S is the square brackets I minus 1. But what we will actually prove, this is actually not without reason that we prove this stricter quantity, because whenever we use a proof by induction, sometimes a stronger claim may tend to be easier to prove. So we will show that for every S subset of M, so any subcollection of indices, probability of AI given Bs is strictly less than 1. Okay. Now, as I told in the beginning, this also is like I wanted you to memorize these notations Bi, Di and Mi. Okay, and also this notation Bs. I also want you to pause and understand that in order to prove this claim, that probability that union of these events is less than 1, it is enough to show that some conditional probability is strictly less than 1. Okay, this also I want you to appreciate, and now we'll only focus on this conclusion. Okay, so here also you can really argue with pictures as to why this expression, this guarantee here will ensure the guarantee that we want. Maybe if you are trying to argue it with pictures, it is better to do this. Right? These two equivalences, showing that this is less than 1 is equivalent to showing that P of Bi given Bs is greater than 0. Now the advantage is that everything now looks like B events, right? So what we are saying is that P of Bi given any intersection of any subcollection is greater than 0. In particular, even if this subcollection is everything else, this is or even including I, this is greater than 0. And now if you expand it using the conditional probabilities, the numerator would be the intersection of all Bi's, which again has to be greater than 0 for this to be greater than 0. And the intersection of Bi is greater than 0 implies union of AI's has probability strictly less than 1. Okay, so I mean, this is, though we did it in a full 1 page, right, it is not very difficult to see at least intuitively that this condition will imply the aim that we want. Okay, so with that, we are ready to state the 3 variants of the lemma and prove them one by one. Okay, so again, remember, even in the versions of the Lovasz local lemma that we are going to state, some things are going to be common, which you already know. The events are A1 to AM, and for each I, there is this subset of indices Mi such that AI is mutually independent to all the events indexed by these subscripts. Okay, all those events Aj where J comes from this set Mi, and our Di is nothing but the remaining subscripts. But by remaining we mean you have to remove I also, and this we just said. So I know I'm banking on the fact that you have already memorized this definition of Mi and Di. Now, what is Lovasz local lemma's version 1, which we will prove? We will set this little d to be the max over I of this Di. This is the same d that we saw in the version that we used in the last class. Okay, the dependency is contained within a set of size at most d. Okay, so the size of Di may be different for each I. We are going to take the maximum degree in some sense. Okay, we can also plot this dependency as a graph. If AI depends on Aj, then you will put an arrow to Aj and so on. And again, this is not exactly correct. You should define this graph by saying that you do not put an edge if from a vertex to the collection of vertices to which it is mutually independent. Okay, again, you have to do a bit of long talking to draw this graph, but yeah, the idea is that this is the maximum degree of that graph. Now, and we will assume slightly stronger bound on P of AI. So this version is in fact slightly weaker than the version that we were using in the last class, but weaker only in the sense that instead of an E, we had to use a 4 here. But remember there was a d plus 1, here it's a d, that makes this slightly better, but let's ignore that. We will only claim that this is a weaker version of the lemma that we have used. Our lemma, we wanted P to be something like 1 by E d plus 1. So instead of that, here we want P to be at most 1 by 4d. Okay, and then what is our claim? Our claim is that the union of events AI is going to be strictly, its probability is going to be strictly less than 1. But after all the massaging, what we have to show is that for any I and any subset of any I in M, in any index I and any subset of indices S, probability that AI given BS is at most 1. Okay, that's all that this at most 1 is all that we really care about showing. But for the sake of proof, this is all that we care about showing. But for the sake of proof, we introduce this guy in between because we are going to do a proof by induction. In fact, we are going to show that it is quite small. It is at most 1 by 2d. We only wanted it to be strictly less than 1, but we will get this to be at most 1 by 2d. And our proof is going to be via an induction on the size of this set S. Okay, so yeah, so we are ready to start the proof. The base case is easy to verify. This is where I wanted you to interpret what is B omega. Okay, so B omega is the universe, it's a sample space, it's omega. Hence, P of AI given omega is just P of AI, right? This is vacuous conditioning. You are just not conditioning at all. P of AI, which we have assumed is 1 by 4d, which we have assumed is 1 by 4d, and that is at most 1 by 2d. So the base case is okay. Now we'll also clear the case when this S contains I also. Okay. Now you see that's a very silly case, right? Because remember BI is the complement of AI. So if this S contained the index I, then you are taking an intersection of events, one of which is AI complement. So, and you are conditioning on that fact, which means if AI complement has occurred, how can AI occur? Probability of AI has to be 0. So that's what is written here. If I is in S, then P of AI given BS is P of AI given an event which is stronger than saying AI has not occurred, okay, AI complement has occurred. So it is 0, which also satisfies what we want. It is strictly, or it's less than or equal to 1 by 2d. So from now onwards, we will assume that this S does not contain I. So in particular, the cardinality of S is at most M minus 1. And hence, we can now split S into, within S, we can identify those subscripts which are in Di and those subscripts which are in Mi. Remember, Di union Mi was not entire M, it had I also, but now that I has been ruled out, we can split S, we can partition S into two disjoint sets of subscripts, which I denote by this clumsy name, SDI and SMI. But I thought about using smaller notations, but then this is meaningful, right? So this S is to indicate that we are not talking about the entire collection of events that AI might depend on, but only those inside of S. The D is for dependent, and the subscript I is to remind you that these SDI and SMI sets are different for different I. Okay. Now we can also make one more assumption which is needed for the induction hypothesis to be on a smaller set. Okay, we are going to use the induction hypothesis on SMI. So we want the size of SMI to be at least 1 less than the size of S. Okay, we will use it later, but this is the reason why the next step is done. So in order to get this set to be strictly smaller than S, we want this set to be non-empty. Okay, so what happens if S intersection Di was indeed empty? Okay, if S intersection Di was empty, then P of AI given Bs, remember this Bs is now a subset of intersection of a subset of events indexed by MIs. But by definition, AI is mutually independent to them, which means conditional probability is same as the unconditional probability. Okay, so this BS is an intersection of events, all of which are mutually independent from AI. So P of this conditional probability is just P of AI, which again we know is half of the bound that we are trying to prove. So here this, in fact, in this part, the key property that we will later use is this. This helps us running the induction. Okay. So now we are ready to. So far we in fact only kind of again treated only the base case and some removed some corner cases. Now we are going to do the bulk work. So P of AI given Bs, this is the event whose probability we want to upper bound by 1 by 2d. Okay, that's our aim. So this we are going to write it as P of AI given this Bs. We know that S is split into, it's a union of SDI and SMI. So if you take Bs, think about it, we can write it as BSDI, which is the intersection of all the events indexed by SDI, intersection with the intersection of all the events indexed by SMI. Okay? It's a simple thing. If it's not clear, then pause and think. Now, this conditional probability, I can write it like this. Okay, this is another verification task for you. P of something like C given D intersection E is P of C intersection D given E divided by P of D given E. Okay. Again, I want you to verify in two ways. First you expand and verify, and second you use a picture or an intuitive understanding of what a conditional probability is. So you can think about this whole thing as you can blow up your E to be omega, and then think of these things as happening inside of the set E. And then this is something which is very similar to saying P of C given D is P of C intersection D by P of D. Okay, so I want you to verify this both by expanding this and later without using any expansion, directly using pictures. Okay, so here C's role is taken by AI, D and D are this and this, BSDI and BSMI respectively. Okay, so I have used this expansion here, and I have to upper bound this by 1 by 2d. So I'm going to upper bound the numerator and lower bound the denominator, right? That's the correct thing to do. The upper bound on numerator is straightforward. So this is again AI intersection something given BSMI. I can upper bound this by probability of AI given BSMI, right? Intersection will only reduce the probability even when conditioned on something. So this is upper bounded by P of AI given BSMI, but this is something which we have already seen. SMI only contains events from which AI is mutually independent. Hence, this conditioning does not change the probability. This is exactly equal to probability of AI, which we know is 1 by 4d. Okay. In fact, here I'm not immediately going to write this as 1 by 2d. I'll retain it as 1 by 4d. Now, what is the denominator? Okay. The denominator is probability of BSDI given BSMI. Okay. So this is the event that none of, because B is the complement of AI and it's an intersection, that's why I'm using the word none of. This is the event that none of the events on which AI may depend has occurred, given none of the events on which AI is mutually independent to has occurred. Okay, that is the interpretation of this thing. But again, we are going to work, we are going to massage this denominator a bit, and we are going to write this as 1 minus P of this complement conditioned on the same event. We have already seen this modification here, right? We have already seen this modification here. So yeah, if you had verified it then, you need not verify this fact again. Right? Now, this denominator, remember, we have to lower bound, which means this negative quantity, or this quantity that we are subtracting out, we will upper bound. What is the quantity we are subtracting out? This guy here. Now, what is BSDI? I am just expanding it, that it is the intersection of all those Bj where the subscript j is picked from SDI. Now, De Morgan's law, complement of intersection is union of complements. Complement of Bj is Aj. That's all that is written here. So we have written it as a union but conditioned on something. Again, the union bound applies here also. Okay. So even in a conditional setting, if if you have a union of events conditioned on some event, I can upper bound that probability by the sum of probabilities of each event conditioned on the same thing. Okay, this is again union bound if you look inside of BSMI. Okay, this is why I keep saying you should think about conditional probability as the usual probability, but where now the role of omega is taken by the conditioning event. Okay, then these start making immediate sense. You can also argue it directly, nothing significant here. Okay, so this is the sum. But now these guys, this is where we are going to use the induction hypothesis, right? These guys are already covered by our induction hypothesis, right? Because remember, our induction hypothesis is for all I, right? For all where is this? Yeah, this is our induction hypothesis. This is for all I in M and for all subscripts S, this is true. Okay, so here now the subscripts is some other set, some B SMI. This J is different from I, but our induction hypothesis still works as long as this SMI has cardinality strictly less than S, which we laboriously argued here, right? Yeah, so because of that, induction hypothesis applies, and I can upper bound each of these guys by 1 by 2D. Okay, so whatever I have highlighted here, I can upper bound by 1 by 2D. Now this is just the size of SDI times 1 by 2D, but size of SDI is at most D. That's the guarantee that the Lovasz local lemmas, this version's hypothesis gives you, right? Each, D is the max of DI. Okay, so I'm just directly, SDI, remember, is a subset of DI, so hence it cannot be larger than DI. So it's at most DI. So this the D cancels out to give you a half, but so this is an upper bound on this guy, which means the denominator is lower bounded by 1 minus half, which is half. Okay, so now for this expression, we have upper bounded the numerator by 1 by 4D, and we have lower bounded the denominator by half. Hence, this whole thing is upper bounded by 1 by 4D divided by half, or this is upper bounded by 1 by 2D. Okay, yeah, let me write it here. So this whole thing is upper bounded by 1 by 2D, and that is precisely what we wanted to show, right? Pre of AI given B, this is 1 by 2. Even if you have verified all the steps in the proofs, and you have followed everything that I said, and also verified these extra things I said, there is still something missing, right? We really do not easily understand what is happening. Okay, so in fact, I tried to spend some 3-4 days trying to give a picture proof of this, but failed. Okay, so yeah, I have, in fact, I have a whole section where which I'll not record. I was trying to think about how Lovasz should have, thought of this proof, and I was trying to give a picture proof, but it's not. I mean, at least I could not find a convincing picture proof or an intuitive proof of this statement. But that is why I thought I'll instead of trying to talk about what is the intuition behind this proof, we'll see this proof repeated twice more, and one of them it is slightly easier to get an intuition. Okay, so yeah, so now that the first proof is done, we are already 30 minutes plus. Let's see the LLL V2. Okay, so in V1, remember each probability in V1, each probability P of AI was upper bounded by 1 by 4D, right? Which means this would actually mean, if I take this guy, which is for any I, if I take all the subscripts in DI and then add their probabilities, this will be at most D times 1 by 4D, because there we also had this bound that DI was at most D, right? So this will be 1 by 4, okay? So what I'm trying to convince you is that LLL V2 is a generalization of LLL V1. The hypothesis of LLL V1 will also imply the hypothesis of LLL V2. Okay, but this is slightly more general in the sense this allows your PAJs or your PAIs to be very different, and what we are saying is that for every I you look at the dependent set of events and add their probabilities, they should all add up to something which is less than or equal to 1 by 4. Okay, so maybe some P of AIs may be larger than this 1 by 4 4D, but here this little d is no more used at all. Okay, because we are this how do you say, this is more like an asymmetric version. Okay, so your probabilities can be larger or smaller depending on the size of these dependent sets in which they participate. Okay, and what is the conclusion? By the way, the remaining context is the same. Your A1, AM, those definitions, DI's definition, they all remain the same. And what is the conclusion? The green part is same as what we had in LLLV1. For every index I and for every subset of indices f, we will show that P of AI given Bs is strictly less than 1. So that much is same. But there, instead of, we showed something like P of AI given Bs was at most 1 by 2D. Now, 1 by 2D also, if you think, happened to be twice this upper bound, okay? And that also came up in the proof, in that last step of the proof. But here we are going to explicitly write it as just twice P of AI, right? So let's see this proof, and then maybe we will come back and try to give some interpretation to this kind of an inequality. Okay. Now, why is twice P of AI less than 1? Maybe I should also say each P of AI is less than or equal, strictly less than half. Okay, maybe we should say that, but it kind of is clear if each AI participates even in one dependent set. Okay, because the total sum is at most 1 by 4. None of the events can be in itself more than 1 by 4. Okay, so this is true except in cases when the dependency graph has some isolated nodes and so on, but then you remove them. Okay, because those events do not depend on anything else, so you can really remove them. So here we assume that P of AI is less than or equal to 1 by 4 for all I. Okay, yeah, that's a minor point. Okay, but forget that detail. What we have now to argue is this 2 PAA is what you should keep in mind. Okay, so now this proof, I thought I'll actually, maybe it's a bad idea. I thought I'll write it live because it's good to kind of, so that you can think ahead of, you should try to think it out faster than what I write. Okay, so what about base case? Again, proof is by induction on S, on the size of S. So base case is S is equal to empty. So what we are showing this P of AI given the universal event, which is nothing but P of AI. We are only saying P of AI given B empty is equal to P of AI, which is less than or equal to twice P of AI, which is true just because P of AI is a positive number. Okay, so base case is okay. And then we claim, what are these small corner case claims that we made? We said that I is not in S, because otherwise this P of AI given Bs is equal to 0, which is less than 2 P of AI that we want. And then we wanted to, then we divided S into some SDI, disjoint union SMI. I was not part of S, hence this was proper partition, and we claimed that SDI is non-empty, right? We claimed that SDI is non-empty. Why? Because otherwise P of AI given Bs is equal to P of AI given BSMI, since the AI is independent of all of B of ASM, all the events here or in any color, in these events, this is just P of AI, which is less than or equal to twice P of AI. Okay. So now if you check in all these kinds, we kind of even bounded it with half of the bound that we are trying to prove. So far we are actually better than this bound by a factor of 2, but the price we will pay will be in the main, the bulk case, not any of these corner cases. Okay, and hence we will assume, so hence we can conclude that S of Mi is strictly less than S. So the induction will apply. Okay. So with this much ruling out of the corner cases, we are now ready to analyze this quantity AI given Bs, which, because our Bs we can split it into S, we can split it into SDI union SMI. This intersection we can write it as these two intersections. Now this is AI intersection B SDI given B SMI by P of B SDI given B SMI. Now this is where we started bounding the numerator and denominator separately. The numerator we need an upper bound. This is an intersection of something, so I can always upper bound it by one member of the intersection even under the conditional world. And B SMI, if you remember, is independent. AI is independent to that, so there is no conditioning required. The same fact we have used here also. But here, here we will stop at PAI. Okay, we will not upper bound it by twice PAI or something. Okay, this is the upper bound for numerator. And this denominator, we will first write it as P of, this is complement under the conditional world, right? So I can write it as 1 minus this, and we will analyze, we will upper bound this quantity here. Our aim is to lower bound the denominator. We will upper bound this, right? So this is equal to, this is a complement of an intersection, which means it's a union of complements. Okay, union of Bj complements, or Bj complements is nothing but Aj, right, given B SMI. So now our aim is to use this union bound in the conditional world and write it as sigma j element of SDI P of Aj given B SMI. Okay, so now we are going to use the induction hypothesis, right? Because we have got back this term in the format that we want, right? Some Aj given some Bs, where now this set is smaller than S. Okay, hence our induction hypothesis will apply. Okay, remember that your SMI is less than size of S, so this induction hypothesis will apply, and I can bound each of these terms, I can upper bound each of these terms with twice P of Aj. Okay, remember. So now this is nothing but 2 goes out. So now do you realize what this is? Yeah, this is exactly part of the hypothesis of our V2. Okay, our V2 says that this sum for any I is at most 1 by 4. Okay, so this is 2 times, this whole sum is what our LLL V2's hypothesis says is at most 1 by 4. So this is equal to half. So this guy is upper bounded by half, which means the denominator, this guy is upper bounded by half, which means the denominator is lower bounded by 1 minus half, which is equal to half, which means this guy is upper bounded by P of Ai, and this is lower bounded by half, which means this whole guy here is upper bounded by 2 P of Ai, and that is what we had to show. Okay, so this is repeat of the same proof, but with a slight tweak. Okay, so it's 44 minutes. Oh God. Okay, so now, but here you should think about this expression a bit carefully. It says that your probability of AI given any other list of events in your collection, by the collection I mean the collection A1 to AM, you can condition on the event that any number of them has not occurred, okay, because these are B's, they are not occurred. You are saying that the probability that AI will occur will go at most, will blow up at most by 2. Okay, so in some sense these are called negative independence and so on. right? When the, here, because there is it's negative because there is a complement happening in the conditioning events. So the probability that AI will occur when in general, what is some P of C given D? How does it compare with P of C? Is it greater or less? Actually, it can be either greater, it can be equal, or it can be either less, equal, or greater. Okay, this is all possible. Equal to happens when there is an independence, but the other cases are also possible, right? So if it is greater than P of C, we say that the dependence of C on D is positive, because once D happens, the probability of C happening increases. If it is less than P of C, then we say that the dependence is negative. Okay, but now with this here, we are kind of, the denominator is a negative of events. So even though there could be a blow up, okay, if we had bounded it by, without this 2, if we had upper bounded it by P of AI, then we will say that AI has a negative dependence on the complements of the others, right? But that's not what we are saying. We are saying it can be larger, but it cannot be larger by too much, which means the AI may be positively dependent on AJ complements, but not by too much. So AI being positively dependent on AJ complements is equivalent to saying that AJ may be negatively dependent on the complements, but not by a huge margin. The blow up is at most twice. Okay, so yeah, so that is where we get this lemma. Okay, now my remaining okay, but I think the next also, because there is no point now recalling this whole step. Okay, so maybe this lecture will go to another 10 minutes, but we will do it quickly. Okay, the LLL V3, I'll not, I'm going to give make it a bit ambiguous in the statement now. The something I will prove later. Okay, but again, this is the context we had. Okay, even if you look at LLL V2, we had an upper bound on some conditions on P of AI and then made this conclusion. Okay, the format remains the same. What is that upper bounding condition? We will write later. Okay, so for all I, P of AI is upper bounded by something, and this something will be less than or equal to this xi that we are going to use next. Okay, yeah, and this is the conclusion for all I. This conclusion should be familiar to you. In fact, the hypothesis is what is new in LLL V3. Conclusion is the same. For every index I, every subset of indices S, probability of AI given Bs is less than 1. What we put in between, in V1 we had put 1 by 2D, in V2 we had put twice P of AI, in V3 we are just putting some xi, that's all. Okay, and this bound on each P of AI will be something that is in fact even smaller than xi, which we will need in all the base cases, corner cases, and so on. So now we are repeating the proof a third time, so I'm going to go very fast. It's again induction on size of S. The base case is easily handled. It is at most P of AI, which is less than xi. But remember this something, yeah, P of AI, which is something which is less than xi. We can again say that I is not part of these subscripts, because if so, then this event had 0 probability, which is also less than or equal to xi. So again, this is a probability. So again, your xi has to be greater than or equal to 0. And then we also claim that S intersection Di cannot be empty, because if so, then again there was an independence here, and this term would be just P of AI, which is within our bounds. Okay, so S gets split into SDI and SMI, and hence your conditioning gets split like this. Numerator by denominator, we have seen it twice already. Numerator is upper bounded by P of AI, we have seen it twice already. The denominator is where we will do the calculation differently. Okay, so denominator is P of BSD given, okay, where did I lose the i's? Yeah, BSDI given BSMI. So let's say this SDI, this SDI is some J1, J2 up to some JL. Okay, yeah, this D is not part of the specification, but yeah, this is the list of subscripts for the events on which AI may depend on, right? So now the denominator is an intersection of events, right? But again, it's in a conditional world, but even in the conditional world, this applies. This is, by the way, this we use the same kind of expansion we used in the massaging part also. So if you had verified it there, it's okay, but it's still good to re-verify it, because you already start with some conditioning. Okay, so this is probability of the first event under the same condition times probability of the second event under the extended condition, which is the old condition intersection bj1, and so on. Okay, so everywhere you see that this guy is just staying the same. Okay, now so here we are going to use our induction hypothesis. So remember, these events are all of the form, all these guys are of the form some p of some bj, right, given some bs, which is equal to 1 minus p of aj given bs, and this by induction hypothesis is at most xi. In fact, that is what this xi we do not know, but this is what we are trying to prove. At most xi, which means this whole guy here is at least 1 minus 1 xj. Okay, at least 1 minus xj. So that's what we have used. The first guy is at least 1 minus xj1. The second guy is at least 1 minus xj2, and so on. The last guy is at least 1 minus xjl. These are all positive quantities. X is between 0 and 1. So you multiply all of them, and this is what you get. Okay, this is j element of sdi 1 minus xi. This is the upper bound. Sorry, this is a lower bound. Yeah, this is a lower bound on the denominator. Okay, so we can now substitute it back. So your numerator by denominator will be upper bounded by p of ai times pi j element of 1 minus xj. And what do we want? Our aim is to show that this is at most xi, right? This is what we are trying to show. So in order to show that, we need, by the way, we really know this p of ai we could bound by something. We did not say what that something is so far because we thought we will reach here and then. Okay, so what we want is we want this to be less than xi, and hence I now know what is the bound on p of ai I should give. I should upper bound p of ai by xi times this guy, right? So the something is xi times pi j element of di. Okay, now let me write it and then talk about it. Why here, if you remember, we had sdi, right? But here I am just using di because I do not even know what is s here, right? And this will only make it stronger. If you are multiplying more terms, then this p of ai will only even further go down. All these 1 minus xi's are quantities which are between 0 and 1. Okay, so if you have such a strong bound, we can keep as small a bound of p of ai as we want. If this works, something smaller will also work. But for the lemma to be useful, we should somehow the p of ai should be large enough so that it is applicable under more context. But in this case, this is a maximum that we can help because this has to be true for every s, including s which is just m minus I. Okay, so there is not much that, in which case your sdi would just be di. So we haven't sacrificed anything here. Yeah, but more than the optimization, what I want to see is this is what something that you will put. Okay, yeah, that's what maybe I would have written that again here. So this is the numerator by denominator, and hence if we choose, right, so this is the key. If we choose this for p of ai, then our claim will fall. Okay, so I'll stop by stating this third version. In fact, this third version is the most, how do you say, that's the most strong version also. And this is, if somebody just says Lovasz local lemma, they mean the third version. Okay, so let me write it in full hence. Let a1, a2, am be the events such that each ai is mutually independent to all events in all events subscript indexed by mi. Then and further, if you have these numbers, real numbers x1 to xm between 0 and 1, such that each probability p of ai is upper bounded by this expression. Okay, it would all, if I had written this lemma like this in the beginning, this would all look like magic. Okay, so but now you should realize that these are what comes out from the proof. I'm slightly being, how do you say, shallow when I say that this just comes out of the proof. You can attribute meanings to that with a lot of effort, but I tried and failed. Okay, so for now, let me say that, okay, at least this expression makes sense if you know how this is proved. Okay, this comes from the bound of the denominator using induction hypothesis. If each P of AI is upper bounded by this expression, then you can have this conclusion that you want, okay, which is that the union of events has a probability, again, the strictly less than 1. But if you redo the proof, and I want you to do that as an exercise, in fact, you can show something more, okay, you can, it's not very important, but you can show that the probability of the intersection of the complement events, which from this it would just follow that it is greater than 0, but you can substitute, can find the expression here. It turns out to be I equal to 1 to m 1 minus xi. Okay, so this you can actually now verify by just expanding this intersection I equal to 1 to m, these are bi's, right, as p of, this is nothing but p of intersection I equal to 1 to m bi, which is p of b1 times p of b2 given b1, etc., p of bm given all the other guys. Now each of them, you know what is the bound that you will get. It is at most is 1 minus xj, right? So these are all lower bounded by, this is just p of b1, yeah, p of b1, okay, these are all lower bounded by 1 minus x2, 1 minus x3, etc. And what happens to p of b1? Okay, p of b1 also I can, even this is just conditioning on the b phi if I want. Okay, so that also I can lower bound by 1 minus x. Okay, so that will give you this expression. Okay, but this is not important. The conclusions, this is important in a sense. It tells you that this exponentially goes down in terms of number of events. So if each xi is something like half, this would be 1 by 2 to the power m. That's as low as this will get. So we are just above 0. Okay. So that for that reason this is important, but otherwise this is okay. And as I told you, this is called the general version or the asymmetric Lovasz local lemma. And by the way, we still did not prove that symmetric version. Why? Because we only proved it with 4, but you can get the symmetric Lovasz local lemma from this third version V3 by setting your xi to be 1 by d plus 1. Okay. So again, you can verify the computation. If you check, put xi equal to 1 by d plus 1, you have to now verify what is this expression, right? This expression, with some, okay, let me say it, okay. It's anyway, I exceeded more, I took more time than what I thought. So now you see what this expression turns out to be. So xi is 1 by d plus 1, 1 minus xj is 1 minus 1 by d plus 1, which is d by d plus 1. And this product therefore is just power of di. Now this I can lower bound by putting an upper bound here. This is a quantity less than 1, so this is in the correct direction, right? This is in the correct direction, and now this I have to lower bound. So what I'll do is I'll take its reciprocal and upper bound. So its reciprocal is d plus 1 by d, which is 1 plus 1 by d, the whole power d, which is 1 plus x is upper bounded by e to the power x. So this is at most e. So this is lower bounded by 1 by e. Okay, so now you see where it comes from, right? This, remember in the general version, your e p d plus 1 had to be less than or equal to 1, which means p was upper bounded by e 1 by ed plus 1, right? So p is a lower bound for this, and p is an upper bound for p of a, right? So you this now if you read together, this means this expression upper bounds p of ai, which means we get the hypothesis of LLL V3. Okay, so from the hypothesis of the symmetric Lovasz local lemma of our last class, we can, with this setting xi being set to 1 by d plus 1, we can prove the hypothesis of the LLL V3, and LLL V3 will tell you that probability of this union event is strictly less than 1, which is the same conclusion that we have in the symmetric version also. Similarly, you can actually prove LLL V2 also from LLLV3, which I want you to do as a exercise. Okay, so this I will leave as an exercise. Okay, so let me stop at the 60-minute mark.